Calculate the period of oscillation of a rod and a spring. So we have a uniform mass rod. The rod is pivoted about some arbitrary point, and then it has a spring connected to it at some arbitrary point, and we let go of this, and it goes back and forth, back and forth. We want to compute the period of oscillation of this. So how do we go about this? So let's say the length of the rod is L, and let's say the distance from here to here is equal to D. So the pivot point is a distance D away from the top end of the rod, and let's say the spring is connected to some distance here. Let's call that Y. Okay, so then how do we compute this? So what we say is, okay, what are the different forces that are causing a torque on the rod that are making it go back and forth, back and forth? Well, we have the weight of the rod. So let's just for a second concentrate on the weight. The weight is, if it's a uniform mass rod, the weight is at the center. We have mg. And the distance from here to here is L over 2, right? So the torque due to the weight is going to be equal to this distance here, which is what? L over 2 minus D, right? This distance, little d. So if you subtract L over 2 minus D, L over 2 minus D, that's the distance from the pivot point to where the center of mass of the rod is. So the torque equals R crossed into F, which equals I alpha. So the general procedure for any kind of problem like this is to get the total torque on the system and then set it equal to the moment of inertia times the alpha, and then do, usually we do some kind of small angle approximation. In any kind of harmonic motion like this, the idea is to make it look like the original harmonic motion with a spring and a block, where we displace a mass m from a spring and we let go. We have force is equal to negative kx, which is equals to ma. And then we have 0 is equal to mx double prime plus kx. So if you go back and look at my notes on simple harmonic motion, you will see that we end up with this. And the solution to this is x is equal to a sine of omega t plus phi. And so what we say is omega comes out to be square root of k over m. And then the period of the oscillation is 2 pi square root of m over k. And so using this result, if we can make any other equation look like that, we can borrow that solution. So in this case, if we didn't have the spring, this would exactly look like that, right? mx double prime plus kx, this is the second derivative of that. So whatever is in front of the theta would take the role of the k. Whatever is in front of the theta double prime would take the role of the I of the pivot point. That would take the role of the mass m. And then we would have omega is square root of k. What's the k here? It's this thing. L over 2 minus d mg divided by I pivot point, right? So we could always keep using that result, make our differential equation look like that, and keep using that result. Now, what's going to happen to now that we have the spring? Okay. Well, now that we've got the spring, we've got to worry about the torque of the spring. Okay. So how do we get that? Well, let's now concentrate on what the spring is doing. We have this is D here, and then the distance from here to the spring is y. So the force of the spring is k times how much the spring has been stretched, right? So when you let go of this, the spring is stretched by a certain amount x, right? So we can say the torque is equal to R crossed into F equals I alpha. R is the distance from the pivot point to the where the string is connected, right? So it's always the same way. Same thing here. R was the distance from the pivot point to where the center of mass of the rod was, right? So it was L over 2 minus D. So in this case, R is the distance between the Y and the D. So it's Y minus D. F is equal to Kx times sine of what angle? Well, then it's you have a R, right? So let's put this in a different color here. We have R, we have F, and then sine of this angle, right? Sine of this angle, and that's equal to moment of inertia about the pivot point again, times alpha, which is the second rate of change of theta, theta double prime. Okay? Well, you know what? Let's give this a different variable. Let's call this one beta. And let's find the relationship between the beta and the theta here. That beta is a complementary angle to theta. Theta is the angle that the rod makes with the vertical as it's rotating. Beta is the complementary angle to that. So we have sine of pi over 2 minus theta. And then we have here, going back to the other color, we have y minus d. Kx is I of pivot point times theta double prime. Now, what's the x? Well, x is the amount that the spring has been stretched. So what's going to happen? As the rod goes this way, the spring goes up a little bit. It makes an arc length like this. Visualize this like this. It makes an arc length. So the amount by which the spring is stretched, x, right, is related to the angle through which the rod goes up, so theta, right? So the amount the amount of the stretch of the spring, x, is the arc length of the circle made by when the rod goes up by a certain angle. So the distance from here to here and the distance from here to here are the same. That would be y minus d. Y minus d. Okay, so we could say x is equal to y minus d times theta. X equals y minus d times theta. Then we have sine of pi over 2 minus theta times I of pivot point. Okay, theta double prime. Now what's going to happen? When we do the small angle approximation, if the angle theta is small, then this is going to be called what? Sine of pi over 2 minus a small angle. That means this thing is approximately what? Well, as the angle approaches pi over, as this angle is small, this whole angle approaches pi over 2, right? That means this angle beta for small oscillations, the angle beta is approximately pi over 2. And that means sine of the angle is approximately equal to what? 1. So that makes the small angle approximation makes this problem a lot quicker and a lot more doable. If beta is approximately pi over 2, sine of pi over 2 is 1. So then this problem looks like basically y minus d squared k theta, right? Of course, again, we're going to put the negative, 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 negative. And then we're going to take it to the other side. And so what's the result that we get? And K is, in this case, the spring constant of the spring, right? So what's my omega going to equal? Square root of K over M, right? K over M. But in this case, what's the K? Well, K is whatever is in front of the theta, right? So the K over M is the generic solution, right? So we have whatever's in front of the theta, which in this case was L over 2 minus D mg. So in this case, whatever's in front of the theta is going to equal Ky minus D squared divided by what, this one is whatever's in front of the theta double prime. So I about the pivot point.